So, first of all, congratulations for getting up early and welcome to the first session of the day. I feel a little bit like cheating myself because of the jet lag. So, I feel for 2 days like having superpower of getting up early after coming from Europe. So, yeah. In this talk, we are going to talk about AI because it's 2026, but we are not going to build any agents or like talk a lot about LLMs. But instead, I would like to bring your attention a little bit more to something called continual learning. Has anyone of you heard about continual learning before? One person. Yeah. So in general, it's like being called the missing piece in training the LLMs and AI currently. So this is the ability of AI to learn and adapt during the process. But today I would like to focus more on the machine learning part. So more the, let's say, classical part of machine learning to show you how does it work, why it's important, and show you in practice how we implemented it in one of the projects in real life in MRI Diagnostics. But we are going to also finish and come back to the LLM part and what's the impact in there. But first of all, I'd like to introduce myself. So, hi, my name is Agata Chudzińska. I came all the way back from Poland, and this is the way how we traditionally smile on the streets in Poland. I have been working over the last years as the CTO and AI solutions architect at an AI consulting company in Hamburg. And I have been working in the AI and machine learning field over the last 10 plus years already. So I've seen the whole spectrum of people 10 years ago saying, no, take the AI from me. I don't want any machine learning. This is too researchy, whatever, towards everyone is expert nowadays, right? Especially on LinkedIn. And we have been implementing quite many different projects over the years. So I work with automotive, telecommunications, e-commerce, and the other ones. But what will be important for the rest of the talk, we also did quite many projects for medtech companies, and we worked also with hospitals. So when I say about the medical projects, I will today mainly mean analyzing MRI, so analyzing the pictures and detecting structures such as bones, or more complicated, detecting all of the small veins in the liver. So this is a project that we also did, and that's super important when you're doing liver resection. Then cutting the wrong vein can have really serious consequences for the patients. And we also frequently build it in mixed reality solutions where the doctors can use it for planning surgeries or for patient education. And today I chose to talk about something called Focal Cortical Dysplasias, which is, I would say, the most difficult project that we had in this area. But before we dive into that, I wanted to share with you some important statistics that I wasn't aware myself before I started working on this project, which is that around 50 million people globally have epilepsy, which makes it one of the most common neurological diseases globally. And if having the seizures wouldn't be enough, then every epilepsy patient is 24 times more likely to die unexpectedly because of something called sudden unexpected death in epilepsy patients. So what are those FCDs? If we take a magnifying glass, we'll see something like that. So these are basically some errors in the brain development or so-called faulty brain tissue, which are a frequent cause of epilepsies, and they are responsible for over 70% of the version of epilepsy, which is pharmacoresistant. So some of the patients can take just drugs and live a normal life. Unfortunately, there is also some big group of patients who cannot do this, and for majority of them, FCDs are the reason. Good news here is that they are potentially operable, but it is not so easy to find them. So how do they look like on MRI pictures? Just very brief course, if you were lucky enough to never have any of the MRI scans being done for yourself, just to be on the same page. So MRI stands for magnetic resonance imaging, and they are being done using the MRI scanners, which you can see on the picture here. So these are basically tubes making strange loud noises. You get in, and it uses magnets and radio frequencies at high speed to create very accurate pictures of the inner body and inner organs. And you can use various settings so that it exposes a little bit different features of the inner body. So if we already have the MRI, let's see how we can find our FCDs. So there are a few distinct features in here. So one of them, quite characteristic, is the blurry boundary, which you can see on the picture here, between the gray and white matter. There are some unusual brain surface foldings, the hyperintensities of the gray and white matter, quite characteristics, the so-called transmantle sign. So this is like visible path towards the central of the brain. But to not make it too easy, they can differ in size, in location, and in shape. And there can be some of the features present, but it's not like check-in that they have to be these 4 features every time present. So it's not a tedious task. But when things go well, and usually epileptologists, but they can be also different doctors who find the FCDs, the patient can undergo brain surgery. This is, by the way, a real one, not AI generated. And the patient can become seizure-free. So I have a special task for you. So knowing everything that you have learned now today, could you take a moment and take a look at these pictures and tell me if any of these 3 patients, and if yes, which one, has an FCD? So a few seconds for you. So, okay, so let's maybe make a quick voting. Who thinks it's number 1? 1%, 2. Who thinks it's number 2? Yeah, we have more people for number 2. And number 3? Okay, so number 2 is our winner. But that was a tricky question. All of you were right. So congratulations. That's the second success of the day after getting up early. Yeah, but what I wanted to show you using this example is it's really not so easy. I mean, we saw these examples on the previous slides, as usually in the medical books, like this is very obvious kind of blurring or whatever. But in real life, it's super hard to find them. I mean, we have worked for a few years on this project, and as programmers, we actually still don't know how to find them, even though we have seen hundreds of those. So, as usually in life, if we have some discipline that requires a very narrow expert knowledge, there are not so many experts who have it, and that's currently an issue. So we have been thinking, how about using AI to find them? I mean, if you think about it, like what's the premise of machine learning and AI? To find some subtle patterns in the data, which are somewhere there, and to actually democratize them in the best way. So it sounded really like the definition of why machine learning was invented for. So we have taken the AI experts from our team. We also work together with the biggest epilepsy center in Germany, which is in Hamburg. And we have also taken real Dr. House to make our chances even higher to succeed. We started with the data set. So if you work with machine learning, data is the king, so it's the most important part. So we managed to collect the biggest to that point data sets of the MRIs with FCDs, and these are 201. If you did something with machine learning before, you might already have the sign, okay, that's really not a lot. And we'll come to that later, why it was so difficult. But we also didn't want to recognize just FCDs knowing that there are some. We wanted it to discriminate. So giving it some MRI series, we wanted to get the information, is there an FCD or not? And if yes, then where? So we also used the normal FCDs, 100 of them. And we also did use different pathologies. So meaning there are some changes in the brain, but they are not epilepsy related. I mentioned the different settings that we have for the MRIs. So we use T1 and FLAIR. So these are 2 of the 3 most popular ones. So the T1 exposes a little bit more the shapes of the inner organs. The T2 that we didn't use exposes the fluids. And FLAIR is a special version of T2, which exposes a bit the abnormalities in the fluids. We also included the suboptimal quality. So if a patient moved a little bit, there was like a little bit additional blurring, whatever. This is what really happens in real life. So we're also taking this. And we really wanted to make sure that we are right here. So we have taken a few different doctors so that they agree that this is really an FCD in there. We also looked at how the seizures look like, because there's also kind of correlation between the types of seizures and if the FCD is present or not, and as well the EEG data. Why it was so difficult? First of all, working with medical institutions is not so easy. If any of you already had a chance to do that, I see a few people nodding here. It's really not so easy to get the data from the hospitals. Second thing, it's really hard to annotate the data. So we really wanted to be sure where it is present, on where the FCDs are. So we really had to have the doctors go through all of the pictures, and usually MRI series, this is like about 200 pictures in one series, and annotated. We of course created semi-automatic annotation methods for them, but it was still quite time consuming. So second step, we have the data. So let's train some neural network. Well, not so easy, although of course we tried, but it turns out if you have not so much data, then you really need to make additional steps to make it work. So we had to take a step back and work with the pre-processing. So prepare a little bit our data for the training. So we did that in 3 steps. First of them was the brain tissue segmentation, which you can see here. It's actually solved task. You can get really high accuracy for this, so we'll not focus on how we did that. But we did that for 2 reasons. First of them was to remove all of the unnecessary data, so the skull and all of the different things, just to make it easier for the neural network. But secondly, we used it as prerequisite for step number 2. And the step number 2 relies on the fact that the epileptologists over the years, they already came up with some methods that were making their work easier. So making some of the methods to expose a little bit some of the features on the images. And one of them are the methods developed by Dr. Huppertz, who came up with a few different ideas and filters, and we're inspired a little bit on that and prepared it also for our solution. So first of them is junction, which you can see on the picture here, and it relies on applying standard deviation and mean on the intensities of the pixels. So it helps us explore this hyperintensity feature that I mentioned earlier. And the second one is quite interesting because the extension, it relies on the idea that if you apply more blurring to something that is already slightly blurry, it exposes the blurring even more. And I also got to know about it at some of different conferences, that it's also the method that you can see to check which of the pictures have been adapted in Photoshop, because it's also creating some additional blurring. So we can also see which areas were adapted in this way. And finally, we prepared the input for a neural network. So we combined it into 4 channels, so the T1 and FLAIR, as well as these 2 additional filters that we created. The neural network architecture. We really spent a lot of different experiments. Here, I will not go by all of the different architectures that we used, but we'll just focus on the one that worked well for us. But it was quite interesting to see that we tried all of the newer architectures, such as the transformers, who are like the backbone right now for all of the LLMs. It didn't work so well as the architecture that we chose here. So this is a variant of the so-called unit architecture. It's the encoder-decoder one, so just very brief intro so that we're all on the same page. So it relies on quite interesting concepts, which is that we're trying to, in the first part of the neural net, we're trying to compress the picture and to encode the information. So we have quite big pictures with 4 channels. And during this process, we're trying to get super many channels, but a very small size of the picture. So it means that we are trying to encode or to compress the most important information, such as like edges and shapes, and to store it in here. And in the next step, based on this, we are trying to decode this information and come back to either original picture or to segmentations that we have here of the FCD. And during this process, when we are training the network, it learns here what are the most important features that are actually describing what we want to get. And this is still one of the most important architectures in the biomedical imaging, even though it's not so new anymore. We also use like variation decoder, but it's just for the training. It was because of the fact that we used not so much data, so we didn't want our neural network to overfit, but it's not influencing the results in any way. So let's take a look at the evaluation. How did it go? So we used the standard metrics such as precision recall, but what's quite interesting and important, especially for the medical images, is also the explainability. So this is a part that I also got yesterday a question, did you use LLMs to solve this task? And I was like, well, we did run some experiments later, but the issue with using LLMs for the medical field, it's quite tricky. We'll also touch on this a little bit later. But the main part is the explainability. You don't know why. So what was very important for us was also to get the segmentation mask, to know which pixel, or rather voxel, so voxel is like pixel but in 3D, is really showing there, okay, this belongs to the FCD and this not. So it really allows us to see why the given decision was made. And it also allows us to actually go through the medical certification process, which otherwise wouldn't be possible. So what are the metrics? We got quite nice recall. So it means like out of all of the FCDs that were there, we detected 70%. The precision 54, it means like how frequently our, like out of all of the guesses or all of the positives that we said are there, how many of them were really true. So it was also quite good. The dice coefficient was lower, but it's really hard on the pixel level to say which thing belongs to this FCD and which not. So it was still quite fine. So as the last step here, we had to go through prospective clinical validation. So you always need to go through this process if you want to apply anything, any model in medical fields. So next to the normal patients who are getting diagnosed normally, we are also checking on the real data, all of the patients coming in, how our model is doing. I know it's a little bit complicated table, but I'll guide you through it. So let's take a look first here. But looking at the columns, so in the middle, we have the ground truth. So we have a few doctors checking if the FCD is there. So we know that there are 9 cases, 9 patients. On the left-hand side, we have the neuroradiologists who are checking and saying what they think if the FCDs are there or not. So they're able to detect 3 of them. And our model was able to detect 7. So there is already quite important improvement in here. But after the initial joy, we also saw that there are quite many false positives, meaning that our models, like there were, of course, no false positives according to the real data. The doctors made 5 wrong answers. In this direction, our model did 86. So it was very confidently and very frequently saying that the FCD is there, which of course is not useful. So we tried to analyze it and we came to a few conclusions. What happened here? So we saw in the moments when our model said, hey, one patient has 2 or 3 FCDs, which technically is possible. So we couldn't exclude this option. It happens very rarely, but still can happen. So these were mainly the cases when our model was wrong. And when it said there is only 1, it was like right in the 86% of the cases. So it was much higher. So what happened here? And this is also one of the important steps that I want you to take from this talk is always try to ask the questions and try to understand why exactly a given decision was made. So we also went by one to understand which factors contributed to that. So first of all, there were the artifacts. So I told you we got all of the data that were there. But if the patient moved, it creates some additional noise in the data, and our model reacted to that. There were also some similarly looking lesions. So not all blurring means automatically it's an FCD. So it reacted to, like in quite a good way to some of the features, but the problem is simply way more complicated. So it was going in the right direction, but still making some errors here. And we have also seen that the distribution was not so good in our data set, meaning that there are FCDs present in some parts of the brain more frequently than in others. So then the model was reacting and saying it's usually always in the same area of the brain. And what we saw as well is that the data distribution, meaning in our case, the majority of the patients in our data set, they were having those FCDs. And then we took some without any anything happening in the data, and we also got those with different pathologies. But it's not how the real life is. As I told you, it's like 1% of global population having epilepsy, whereas our data set, it was like the majority of it. So that's what happened here, and what actually was where we are wrong. So let's finish this part with the challenges that we're having. So we have quite many false positives, which is making it a little bit like useful for initial pre-screening, but if you get too many positive recommendations, you at the end of the day, you don't react to that. We have data collected only in one hospital, so there is low variance of the scanner's use, meaning if we go to the next one, it can work, but maybe there will be some issues because the data will be a little bit different. I know I'm Captain Obvious saying that the medical data are very sensitive, but it will be also very important for the later part. And we'll also have very strict requirements because of medical certification regulations, which, again, the point that we touched already. For example, we always need to have all of the details about the patients that we are training. So whenever we are training the models, we always need to have the data about the real patients, about our population, because otherwise we simply cannot certify it. So you cannot use LLMs right now to do this work because you have no idea which data was used in there. So that's why that's also a tricky part when working with this area. So we were thinking, okay, what can we do more? And we came up with the idea, how about using continual learning? But before we dive into continual learning, let's just revise a little bit the typical flow when we're training machine learning models. So we first of all need to understand the problem, what we already did with epilepsy. We create our data set. We train the models to do different experiments. We deploy our model, and we live ever happily, our model working in production. This is usually the part that I'm hoping to some people just to smile or laugh. Fortunately, you also did, so that's not how it is in real life, of course. Why is that? Because of a few different things. So first of all, it's the data drift, meaning our data for sure will change. We'll have new patients, new scanners. If you're doing recommendations, your users will start to behave differently. If you're doing fraud detection, the fraudsters will, of course, start using different methods. So no matter what, the data will change. You might also want to add new classes. So I told you we're doing different medical projects. So for example, we also did brain tumor segmentation. So how about detecting the different things if we are already developing our models, or detecting the different pathologies in the brain that I mentioned? We might want to add a new task. If we already have a model, I don't know, making summarization of the text, how about extracting some additional data if you're already doing similar things? We'll always have bias in the data. So it will never cover all of the possible cases. It will never cover all of the possible things in the population. So this is something that for sure will happen. And in general, all of them will contribute to the fact that our models will decrease in performance. So we have a few different approaches how we can attack this problem. So first of them is the so-called transfer learning, how we call it machine learning. But nowadays you could think about it more as fine-tuning. So the idea here is, let's take a pet example here. So assuming you have a cat and a dog, and you want to train a small neural network to recognize the pictures of your pets. And it does it quite well until you buy a guinea pig. And now your model has a great idea of what a cat and a dog is, but as you didn't use your guinea pig in the training, it doesn't know anything about it. So the idea here is, if we already have a model that's recognizing these pets, there are so many similar features that the guinea pig is sharing with them, like having faux paws, being cute, fluffy, and all of the other stuff. So let's just take this neural network that we already had, feed it with just a few examples of a guinea pig, and have a very decent guinea pig classifier. And it works very well. But what will happen is that our model, unfortunately, will get much worse on the cats and dogs. So what we see here is the phenomenon called catastrophic forgetting. And this is the central area that continual learning is trying to counterfeit. So we can see it looks a little bit more smart on the graph here, but let's analyze it. So let's assume we have the first task, which is the cats and dogs classifier, and it gets very well in short time, whereas the second task, the guinea pigs, is like on a 0 because it haven't seen it at any point. And in the moment when we get this model and we try to train it further, it gets quickly very well on the second task, but it forgets a lot about the first task. Why does it happen? Mainly because we're again trying to adapt a little bit our neural network. So it means we're adapting the weights. So we're adapting the parts of the neural network that was very well on the first task, and we're messing around with it. And there will be a few methods that help us to counteract this. So let's come back to how we can solve our issue. So the second idea is, how about just taking all of the data? I mean, we still have the pictures of our cats and dogs, so let's just take them, get the guinea pigs in, and train one model from scratch. Does it solve the problem? Yes, it does. It is actually the best solution to this problem. But if we would like to come back to, like, out of this pet example and back to the real life, we'll have a few issues. So first of them, it means that we need to keep all of the data forever. I mean, as long as we'll maybe try to train a new model, which is raising some serious privacy concerns, especially if we're working in the medical field. Secondly, not so important for the pets and maybe not for our epilepsy, but if you think about much bigger models, training them from scratch each time, it's really causing significant cost of computation and storage. Connected with that, of course, carbon footprint for the GPU training, and training each of this model takes a lot of time, which you don't always have. So this is where continual learning comes into play. And the main idea of it is that the models should be able to adapt to the changing conditions and learn continuously, without forgetting what they learned in the previous task before. Moreover, they should be able to reuse the knowledge that they already have so that it's easier for them to learn the new skills. So it's how we humans do learn. And that's why many continual learning methods are inspired by biology, and we're going to see that. And moreover, continual learning is also being considered one of the key aspects of intelligence. So this is also the fact that what I mentioned at the beginning, it's also the missing piece of why the AI models that we're taking right now are not moving forward so fast, and this is the piece that we're actually missing in there. So we can again make it look a little bit smarter and present it on the graph. So what we want to achieve is that we would like to get a stateful training. So in the stateless one, we always get the same data, maybe moving a little bit in time with the window of the data. But in a stateful one, I want to train one model and then just use small batches of the data and adapt them without touching this data at all. And we have three main areas or three main methods that we could use in continual learning. First of them is the regularization-based methods. So the idea here is that we'll penalize the model for adapting the parameters that are important. So that we still keep the model saying, hey, this task is still important. It's very interesting how it works as well in biology. So it's being compared to the synaptic consolidation. So the scientists made quite interesting experiments in which they were looking at the mice, and when they were learning the new skills, they were having new synapses being created, so new connections between the cells in the brain. And what was interesting is that in the moment when the mice were learning new skills, the synapses were being created, the brain was a little bit trying to avoid them to interact with the different neurons. So it was protecting them to still being in there. And in the moment when this connection was cut, physically, the mice were forgetting the skill. So it's the kind of protection of the brain that's also being mimicked in the area of the regularization-based methods. And how we do that in machine learning is that we're trying to weight the importance of the parameter of the parts of our neural networks, and then during the training add additional regularization term, so that we're protecting the important parts from getting destroyed or getting modified. You might ask how we do that. There are methods that you can calculate. So you can actually calculate in a neural network which parameters, which weights are important for the given skill, such as visual information metrics, for example. What is the issue here? The forgetting is not fully eliminated. So it's usually the first method that you start with. It's helping in quite many different cases, but it works better for tasks that are similar to each other. The next area of methods are the replay or memory-based methods. So the idea here is that we can still store some of the data in our memory buffer so that the model doesn't forget, hey, you still need to do this area and you still need to be good on this data before. And the inspiration here comes from the role of sleep. So when we're sleeping, our brains are replaying, again, all of the memories that we had from during the day, all of the situations. And based on this repeated activities, we are learning and creating our memories. And that's why, again, why children need to and do tend to sleep much more. Hopefully you as well after the conference to build up your memories and to build up, and to learn more during the sleep after it. What's the issue here? First of all, we cannot put everything in memory because there is still some limits in our memory buffer. And the second issue is the data privacy. I mean, still, again, we cannot store forever some patient's data in the memory buffer. So that's, again, an issue. But there is interesting subcategory being very popular lately, which is let's use the generative models to create this imitation of the data. So we can create synthetic data that mimic very well the original ones, and we can store them in memory buffer without any issues. And the last area are the architecture-based methods. So the idea here is that we can adapt the architecture of our neural network to adapt to new tasks that we're adding here. So one of the methods is the dynamic network expansion, which relies on the fact that when growing, when learning new things and adding new tasks, we're just giving next layers of neurons or next components. And then inspired as well by biology, here by neurogenesis, where the brain is adding new neurons, especially in hippocampus, to prevent forgetting. But the assumption here is usually, especially for the classical methods, that we usually should know exactly in front the task boundaries. So which is the task that we want to do, which, for example, in LLMs, it's really the main idea here is we want to do whatever task using one big model. But we'll also at the end discuss the newer methods that work a little bit differently. Okay, so let's come to our problem with the FCDs, and let's see how did continual learning help in our case. So we started here again with our data set, but now we know that it was our fault to create the wrong data distribution, so now we learned and we adapted it to mimic better the real life, meaning the FCDs are now in minority. So we have 30 FCDs, 150 normal MRIs, and 120 non-FCD with pathological MRIs as well. And we divided them into 3 distinct data sets to use for the continual learning. So now we see that it's 10% of the FCDs, 50 normal, 40 different pathologies in each of the data sets. And in our case, we decided to start with the regularization-based approach, more specifically the elastic weights consolidation, because we are dealing with the task that it's very similar to what we had before. And so we adapted just the data distribution or created some of our team members said it's actually a little bit a new task. So first of them, we wanted to recognize the FCDs. And now we want to discriminate from the cases which are false positives. So what was our training strategy? We started with phase 1, which was exactly everything what we covered in the first act. So here we had a baseline data set. We trained a neural network. We got the base model, and then we evaluated it with the data that we just covered. So let's start with the first step of our new experiment, meaning we're taking the first 100 MRIs from the three sets that we had. And first of them, we just wanted to see how does this old model work with the new data. So we just used it in a validation. We saved the results. And then we used the same data to conduct the first phase of our experiment. So first of them was the idea, let's see if we were able to keep all of the data forever. But of course, we did have all of the necessary permission to do that. And let's see if we used all of the data that we had so far, meaning we take the baseline data set, so what we had before, we added this 100 MRIs that we have now, we retrained further our model from the first act, and we got a new model, which we nicely called OVD because we wrote a scientific paper about it, but let's call it for our needs the old data model. We don't need to be fancy. And in the second training strategy, we wanted here to apply the continual learning. So we just have taken this 100 MRIs and we trained further the model. So the model now doesn't see at all the previous data. So it's privacy friendly, etc. Again, let's call it continual learning model. In the second phase, we have taken the next 100 MRI series, and we again run the evaluation. So we saw the first model from the first act, and then we have taken the old data model, the continual learning model, and we just evaluated and saved the results. And here we repeated the same procedure that we did in the first phase, meaning we added a new data set. We gave to the model all of the data that we had from the beginning, trained the model, saved here the model. And in the second one, we have just taken the 100 MRIs that we had. We had the continual learned model from the previous step. So we trained it continuously further, and we got the second version of the model. And finally, for the third data set, we could only do the evaluation. So we have taken all of the newest version of the model, evaluated them against the data set. And let's take a look what the results were. So the results were very encouraging. Actually, they are much better than what we expected. And the funny things or interesting things that we can see here is that the first model, it behaved exactly the same way it did before, meaning it was really good at recognizing the FCDs. So it recognized 9 out of 10, but it was really bad at the false positives. So it was, again, very frequently saying there is an FCD even though there was none. For the old data model, we managed to recognize after the first training 8, in the first run 10 out of 10. So it was really great to recognize all of them, but being much better at the false positives, but still there is room for improvement. And when you look at the continual learning methods, it was again quite in line with when it comes to sensitivity to detecting all of the FCD. So it was 8 and 9 out of 10. And it was much better when it comes to false positives. So we got 70% for the specificity, which is very good results. And of course, we tried to analyze why it happened. So additional observations were that still our continuously learned model was detecting just different brain pathologies. So if we were just trying to make it, hey, FCD or not FCD, healthy or just FCDs, we would have taken about 90%. So that would be much, much better. As the training progressed, we also saw that the model is less reacting to these specific regions of the brain that were problematic before. And what were the conclusions? So first of them, we got very similar level of sensitivity. So we can say, hey, but this model got better results here than this one. But assuming these are just 10 FCDs that we're considering, all of the doctors said, okay, it's actually the same one. We can treat it on this amount of data as very similar results. We got significantly higher specificity, and quite important but not so obvious here, we think that our model is much more robust to any further changes. So if we were about training this model for, 10 additional experiments, adding it more and more data in the distribution where FCDs are in minority, at some point it would say always there is no FCD in there, and it would be right in 90% of the cases, right? So it's this classical imbalanced data set problem. So what we think is quite interesting, and it will come also on the next slide, is that it's very interesting in the area when we're talking about the imbalanced data set to use continual learning to first train the model to recognize very well the specifics of the given class, that is minority, and then adapt it in the next phases to learn what is the normal distribution, while still keeping the model to remember what are the specifics, what are the features of the class that we want to detect. And yeah, we ended here with the fact that our model is currently useful for daily clinical practice, and it's also very helpful for the early detection of FCDs. Of course, not with the aim of right now doing the work for the doctors, but just to being helpful for the initial pre-screening, for example, for neuroradiologists who are not experts, so that more patients can get the right diagnosis and be redirected to the specialists, to the experts, to get proper diagnosis. Because right now, the majority of the patients with FCDs, they never get right diagnosis. So we hope that this work can contribute, for the better of the patients. If you would like to get to know more details about it, we have published 2 papers in epilepsy research. So this is one of the most well-known journals in the field of epilepsy. But if we want to sum up the continual learning, it's not only about medicine. So we have quite many practical examples of it. So first of them is the privacy-first environments. So the situations in which we cannot save all of the data in the buffer and keep the data forever. Second one is the dynamic personalization and streaming data. So this is the situation in which we don't have time to retrain all of the models. So these are the high velocity data, which makes just training it each time from scratch too long. Like we need to adapt more quickly. So using continual learning for that, we can just use small batches and get better in time. The third one was the non-obvious one that I just mentioned, was connected with the fact that we can work with imbalanced data sets, first learning about the specific features and then adapting it to the distribution, as in our case. But I think any kind of industrial IoT cases is also quite interesting to check this method. And I want you to take as takeaway that continual learning is actually not nice to have, but it's actually quite important strategic architectural choice for any production level machine learning systems where the data is evolving, and the data is always evolving in this type of systems, where the privacy is really counting a lot and we have quite high cost issues. But yeah, probably quite many of you already thought, right, it sounds interesting, like training from scratch takes a lot of money, takes a lot of time. The promises sound very interesting here. So how about applying this in LLMs? Well, it is actually a very important part of the research happening right now. And as far as I know, none of the big companies achieved the level in which the continual learning is working for LLMs, although there are many of them trying. Why is that? Because if you attended, for example, the session of Michel yesterday, or if you attended any of the sessions or learn more about LLMs, you know that LLMs is not just one training. It's actually a set of different training sets, let's say. So we have we could do the continual pre-training. We have the instruction tuning. We have the alignment. So there are different steps that we're doing the model training. And it turns out that if you try to tweak one of them, it can also impact the other ones. So it's not so easy to use this kind of methods to adapt it. And they are quite interesting new areas of research which are trying to counteract it. Because if we think about it this way, like being able to adapt and to learn to new circumstances is actually what makes us as humans effective, and how do we thrive, how do we move forward. And if we would like to have models that are truly intelligent, then actually continual learning is something that is super important to implement. And just to finish on that, there is also, I mentioned there is quite a lot of research happening, and I think one of the most interesting parts is from November last year, being developed by Google Research. These are the same research institute that came up with the attention is all you need, the famous paper that introduced the transformers. Some of the people are saying this is the second part, let's say, same level of importance that might get in some time. It's about nested learning. So this is a new paradigm for continual learning that they introduced. And the idea here is very, very interesting because it relies on the fact that it says how we are training machine learning models is actually not optimal and let's do it differently. So they say machine learning shouldn't be treated and the LLMs shouldn't be treated like let's train one big model and do it as one optimizing problem. What they say is let's do instead run a few smaller optimization loops because right now we're having like one big architecture. So we're differently treating architecture, differently training and optimizing the weights. What they're saying is let's combine this because they interact with each other. So they say let's have a few optimization loops and let's try to run them together. Additionally, what they propose is that some of the loops should update faster and some of them slower. So not sure if you know the concept of system 1, system 2 thinking. Scott Hanselman was also mentioning it. It's quite famous theory of David Kahneman, which says that, we as humans are also learning at different speeds. And the idea here is that we should train the models in a similar way. And this is also quite interesting link that they're making to amnesia. And I think some particular type of amnesia. They're saying, if you have it, you actually still have the long-term memory, meaning what you learned before, you still have it. You still have the short-term memory, meaning what you're doing right now, you know about it. But you're missing the mechanism of putting the information from the short-term memory to the long-term memory. So you forget about, like, if you do it right now, you keep it in mind, but you don't remember about it a few days later. So they're actually comparing that current LLMs do suffer from amnesia of this type. So they also are trying to make the concepts of actually trying to solve it, proposing the nested learning paradigm. And they also propose new deep optimizers. So instead of using Adam and the different optimizers that are quite popular right now in all of the neural networks, they're also proposing a new, more expressive ones. And they also developed a proof of concept of the architecture that is self-developing. So it's self-modifying and adapting, having right now already some promising results, but still being on the research phase. But I really do think that's interesting. That's interesting research. That's interesting parts to learn, to follow. And let's see if they'll achieve on what's in there. And I really hope that, and I really believe that the next wave of AI that we'll be having will be connected with applying continual learning and the promises of it to build truly intelligent systems. And what we can see as well from the DeepMind, we see from some of the researchers in there. So they compared that 2024 was the year of agents. Then later we had the year of reinforcement learning, and they claimed the 26 to be the year of continual learning. So let's see what they're cooking. Hopefully it will be interesting. So with that, thanks a lot for your attention, and have a nice rest of the conference.